The sun sits there, 93 million miles away. You wake up, check your phone, fly across continents, watch satellites beam signals from orbit. None of it works without that yellow ball playing nice, but the sun doesn't always play nice. Every 11 years it flips its magnetic field, twists itself into knots, and throws billion-ton clouds of plasma at Earth. Some storms brush past, some knock out power grids, some could end the internet. Which ones should you actually care about? What happens when the big one hits during your lifetime? Where do you hide when the northern lights appear in the Caribbean and your GPS says you're in the middle of the ocean? Your phone goes dark, the power flickers. Then someone in Iceland posts a photo, brilliant green sheets rippling across the sky. You're in Texas. It's not supposed to happen, but it just did. On May 10th, 2024, a geomagnetic storm slammed Earth with a KP index of 9, G5 on the NOAA scale, the most powerful since the Halloween storms of 2003. Auroras appeared in Puerto Rico. In 24 hours, Earth's magnetic field got hit by multiple coronal mass ejections, CMEs, traveling at 750 to 950 kilometers per second. Disturbance storm time index bottomed at negative 371 nanotesla. That's the third strongest reading since measurements began in 1957. Starlink satellites degraded but stayed up. John Deere tractors lost GPS precision for hours. Hydro-Quebec stayed online this time. They learned from 1989. Power companies across Canada monitored in real time. No 9-hour blackout. But it was close. If you value documented solar physics and space weather history like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's Goddard Space Flight Center Heliophysics Division, published May 20th, the Star 2024 in their Storm Analysis Report, and the peer-reviewed study in Journal of Geophysical Research Space Physics from February 2024, documenting the disturbance storm time measurements from multiple magnetometer stations across 6 continents. The British Geological Survey recorded 3.5 volts per kilometer in the Shetland Islands, unprecedented in their measurement history. Now back to the information. 7 types. 7 ways the sun can wreck your day. Let's start with the quiet killer. Number 1. The high-speed stream from a coronal hole, dark patches on the sun, not actual holes, regions where the magnetic field opens to space. Temperature drops from 2 million Kelvin to 1.5 million. Density falls by 30%. But the wind, it accelerates. Coronal holes last weeks, sometimes months. The big polar holes expand during solar minimum, reaching down to 30 degrees latitude. When they face Earth, the fast solar wind, 600 to 800 kilometers per second, slams into the slow wind ahead of it. That collision creates a compression region, CIR. Co-rotating interaction region. The magnetic field doubles in strength, particle density spikes, Earth's magnetosphere gets squeezed, minor to moderate geomagnetic storms, G1, G2, auroras at high latitudes. The catch? They're predictable. Same hole rotates back every 27 days. Same disruption. Communications degrade over the poles. HF radio drops for hours. Aircraft reroute away from transpolar flights. Satellites burn extra fuel to maintain orbit as atmospheric drag increases. Not catastrophic, but persistent. During solar minimum, these streams cause more geomagnetic activity than anything else. The physics behind it? Open magnetic field lines. Unlike the closed loops that arch back to the solar surface, these field lines extend straight into interplanetary space. No magnetic confinement. The plasma escapes freely. Solar wind density in coronal holes drops to 3 particles per cubic centimeter compared to 10 in normal solar wind. But velocity? That's where it matters. Normal solar wind crawls at 400 kilometers per second. High-speed streams punch through at 800. Peak velocities have reached 1,000. The stream interaction region forms roughly 1 astronomical unit from the sun. That's about halfway to Earth. The fast plasma compresses the slow. Density increases by a factor of 3. Temperature rises. The interplanetary magnetic field strength jumps from 5 nanotesla to 15. When that compressed region hits Earth's magnetosphere, the bow shock moves inward. Satellites in geosynchronous orbit that normally sit inside the protective magnetosphere suddenly find themselves exposed. In October 2024, an equatorial coronal hole 30 degrees wide triggered recurring G2 storms over 5 solar rotations. Power grid operators in Northern Europe reported fluctuations every 4 weeks like clockwork. Researchers at the University of Colorado Boulder's Laboratory for Atmospheric and Space Physics documented wind speeds peaking at 720 kilometers per second. The stream lasted 4 days each rotation. During 2024 and 2025, the European Space Agency's swarm satellites measured atmospheric density increases of 50% during each passage. The International Space Station burned extra propellant 4 times in November 2025 to counteract increased drag from consecutive high-speed streams. Each reboost consumed 20 kilograms of fuel. The station typically reboosts once per month, 4 in 3 weeks. That's the cumulative effect. One stream ends. 27 days later, the same hole rotates back, another stream, then another. For months, some coronal holes persist through multiple rotations, up to 6 months during solar minimum. That's 26 recurring storms. 26 rounds of satellite drag, 26 disruptions to polar communications, predictable, manageable, until it pairs with something worse. Number 2, the isolated coronal mass ejection, 1 billion tons of magnetized plasma, launched from an active region. Solar flares twist the magnetic field until it snaps. Magnetic reconnection, energy release equivalent to a 10 megaton nuclear weapon. The plasma cloud races outward at 250 to 3,000 kilometers per second. If it hits Earth, arrival time ranges from 15 hours to 5 days. The magnetic field inside the CME determines damage. Earth's field points north. If the CME field points south, BZ negative, they connect. That's when things break. Here's the mechanism. Coronal mass ejections form when stressed magnetic field lines in the corona suddenly reconfigure. Picture a rubber band twisted beyond its limit. It snaps, releases energy. The plasma that was trapped along those field lines gets flung into space. The magnetic field embedded in the plasma determines its structure. Sometimes it's a flux rope, a twisted cylinder of magnetic field with plasma flowing along it. Sometimes it's a cloud with complex internal structure. The field can point any direction: north, south, east, west, rotating. When the CME leaves the sun, observers use coronagraphs to measure its angular width. Partial halo affects maybe 30 degrees of the solar disk. Full halo expands in all directions. Full halo CMEs aimed at Earth are the dangerous ones. They carry more mass, more magnetic flux, more energy. The CME also creates a shock wave ahead of it, like a sonic boom in space. That shock accelerates particles to relativistic speeds, solar energetic particles, protons mostly. Those particles arrive hours before the CME itself. First warning, March 24th. 2024. Active region 3605 produced an X-class flare. The CME arrived 3 days later. G4 storm. Severe. NOAA space. Weather Prediction Center issued warnings to satellite operators and power companies. The impact compressed Earth's magnetosphere from 10 Earth radii down to 6. Auroras appeared in Scotland at 51 degrees north magnetic latitude. GPS degraded across polar regions for 18 hours. The CME's magnetic field reached negative 35 nanotesla BZ at peak. That's strong southward component, maximum coupling with Earth's northward field. Magnetopause, the boundary between Earth's field and the solar wind, compressed to 6 Earth radii. Normally it sits at 10. Satellites in geosynchronous orbit at 6.6 Earth radii suddenly found themselves outside the protective bubble, exposed to direct solar wind, energetic particle bombardment, single event upsets in memory chips, star tracker cameras blinded by proton impacts. 3 commercial satellites reported anomalies, 2 recovered, 1 lost attitude control for 40 minutes. The fastest CME on record, August 1972, reached Earth in 14.6 hours, traveled at 2,900 kilometers per second. The flare was estimated X20. That storm detonated magnetic influence sea mines off the coast of North Vietnam, permanently disabled at least 1 satellite. The AT&T long-distance telephone network experienced disruptions, but it wasn't a direct hit. The active region was at the limb. Most of the plasma missed Earth. If that X20 flare had been dead center facing us, with a 15-hour travel time, different story. The CME would have been full halo, all that mass aimed directly at us. The magnetic field orientation would have been more favorable for reconnection. The compression of the magnetosphere would have been extreme. Power grids in 1972 weren't as interconnected as today. Fewer satellites, less GPS. Now, an X-20 CME aimed straight at us with Bézi heavily south would trigger cascading failures across every high-voltage transmission line from Quebec to Texas. The induced currents in the ground during the 1972 event peaked at 10 amperes in a buried cable in Alaska. A direct hit would have pushed that to 50. Transformer cores would have saturated in minutes, not hours. Minutes! If you value this level of detail about space weather impacts, subscribe to support the research. Comment your location. This section draws from NOAA's Space Weather Prediction Center Historical Storm Database, updated through November 2024, and the March 1989 geomagnetic storm post-event analysis published by Hydro-Quebec in 1990, documenting the 9-hour blackout and equipment damage across 66 substations. Now back to the types. Number 3, the cannibal CME. This is where it gets mean. Multiple eruptions from the same active region. The first CME moves at 600 kilometers per second. The second launches 12 hours later at 900. The third at 1200. The faster ones catch the slower ones. They merge. One massive wave of plasma with complex, tangled magnetic fields. The shocks pile up. The magnetic field strength triples. When it hits Earth, the impact is amplified. The formation process is violent. The first CME clears out the ambient solar wind, creating a lower density corridor, less resistance. The second CME travels through this evacuated space, maintaining higher speed for longer. It catches the first CME somewhere between the Sun and Earth, typically 0.5 to 0.8 astronomical units. The collision compresses both structures. Magnetic field lines from both CMEs twist together. The combined magnetic flux is stronger than either alone. The shock waves merge into a single, more powerful shock. Particle acceleration increases. The energetic proton flux doubles or triples. And the most dangerous part? The magnetic field orientation becomes unpredictable. One CME might have had northward bezies, the other southward. They merge and rotate. Earth gets hit with a field that changes direction every hour. South, north, south again. Each time it goes south, the magnetosphere couples. Substorms trigger. The ring current intensifies. Then it goes north. Brief recovery. Then south again. Multiple impacts. Multiple compressions. The magnetosphere never fully recovers between hits. That's why cannibal CMEs produce longer, more severe storms than single CMEs of equivalent mass. May 10th, 2024, the Mother's Day storm. At least 5 CMEs launched from active region 3664 between May 8th and May 10th. They merged into a triple cannibal CME. The combined shock reached Earth in under 18 hours. G, 5. Extreme. KP equals 9. Disturbance storm time index, negative 371 nanotesla. Auroras in Alabama. In Mexico. In northern India at 28 degrees magnetic latitude. The British Geological Survey warned it could reach G5 before impact. First such warning in 2 decades. European Space Agency's Gaia spacecraft experienced electrical problems. NOAA's GOES. Satellites measured interplanetary magnetic field strength of 73 nanotesla, with BZ reaching negative 50 nanotesla. That's southern orientation, maximum coupling with Earth's field. The solar wind speed reached 950 kilometers per second. Particle density spiked to 40 protons per cubic centimeter, 8 times normal. The combination created a ram pressure on the magnetosphere exceeding 20 nanotesla. Compression was severe. The magnetopause moved inward to 5 Earth radii. Satellites in medium Earth orbit experienced direct solar wind exposure. GPS constellation satellites reported navigation errors. The auroral oval expanded from 70 degrees latitude down to 30. Duration? 42 hours of elevated activity. The main phase, when the disturbance storm time index dropped below negative 100, lasted 18 hours. That's triple the typical duration. Why? Because each successive CME impact restarted the main phase before recovery could begin. November 11th, 2025. Active region 4274 produced an X 5.1 flare, strongest of solar cycle 25 at that time. 2 earlier X-class flares on November 9th and 10th launched CMEs ahead of it. The forecast models showed them merging just before Earth impact. G4 watch issued. The 3 CMEs contained an estimated 15 billion tons of plasma combined. 15 billion tons, that's 30 trillion pounds. All of it magnetized. All of it racing toward Earth at over 1,000 kilometers per second. If they formed a complete cannibal structure with aligned magnetic fields, auroras would have reached Texas. The mechanism is brutal. Each successive CME acts like a snowplow, compressing the plasma ahead, strengthening the magnetic field, creating a shock that propagates faster and hits harder than any single eruption could. The first CME from November 9th traveled at 700 kilometers per second. The second from November 10th at 900. The X 5.1 CME from November 11th launched at 1400 kilometers per second. Simple math says the third catches the second 30 hours after launch. The combined structure catches the first 36 hours after initial launch. Time to Earth. 48 hours total from first CME. All 3 arrive nearly simultaneously. Triple impact, triple compression, triple damage potential. Number 4, the radiation storm. S in scale, S1 through S5, solar energetic particles. Mostly protons accelerated to near light speed by the shock wave of a CME or the magnetic reconnection in a flare. Energy levels from 10 million electron volts to several billion. They travel fast, really fast. 500 million electron volt protons cover 93 million miles in 20 minutes. The lower energy stuff takes hours. When they hit, they don't care about your magnetic field. They punch straight through to the poles, ionize the atmosphere, and wreck everything at flight altitude. S1 is minor. Proton flux reaches 10 particles per square centimeter per second per steradian at 10 million electron volts or higher. Happens 50 times per solar cycle. Weak HF radio degradation. No biological effects. S2, moderate. Flux hits 100. Single event upsets in satellites. Small effects on polar cap navigation. Passengers on transpolar flights get elevated radiation. 20 to 30 microsieverts per hour. That's the dose from a chest X-ray spread over 10 hours. S3, strong. Flux 1000. Biological effects start. Radiation risk for flight crews. Satellite orientation systems glitch. S4, severe. Flux 10,000. Memory corruption in satellites. Complete HF blackout over polar caps for hours. Commercial aviation reroutes around polar regions. Radiation at flight altitude exceeds 80 microsieverts per hour. S5, extreme. Flux 100,000. Satellite failures. Biological hazard to astronauts. High probability of losing solar panel efficiency permanently. March 15, 2024. Multiple long-duration C-class flares from a region beyond the West Limb sent proton flux above S1 levels, starting at 2050 UTC. It stayed elevated for 72 hours. November 11th, 2025. The X5.1 flare from region 40-274 triggered a ground-level enhancement. Protons penetrated the atmosphere all the way to the surface. Neutron monitors around the world detected the spike. Professor Clive Dyer of Surrey Space Center called it very significant. These are rare. 73 ground-level enhancements recorded since measurements began. Blue Origin postponed a rocket launch. NASA warned elevated radiation would affect spacecraft during the event. The most powerful radiation storm ever measured, February 23rd. 1956, ground-level enhancement, 05, GLE 05. The Leeds neutron monitor recorded an increase of 4,500% above background, 50 times normal cosmic ray levels. The event came from sunspot group 17351 in the northern hemisphere at 22 degrees latitude. The spot group exceeded 1,700 millionths of the solar disk area, massive. The flare wasn't well documented. No X-ray measurements existed yet. But the proton flux at energies above 100 million electron volts exceeded every event since. The spectrum was extremely hard, meaning lots of high-energy particles. The most remarkable feature, a narrow beam of ultra-relativistic particles arrived at Earth within minutes of the flare. The beam width didn't exceed 30 to 40 degrees. It lasted maybe 10 minutes. But in those 10 minutes, detectors across Europe registered increases that have never been matched. 13 neutron monitors tracked it. Ottawa at 1 gigavolt cutoff rigidity. Norikura, Japan at 11.35 gigavolts. The geographic spread allowed researchers to reconstruct the angular distribution of incoming protons. The prompt component had an exponential energy spectrum. The delayed component was power law. 2 different acceleration mechanisms. Researchers analyzing the data in 2005 through 2020 concluded the prompt beam came from magnetic reconnection in the corona, direct acceleration at the flare site. The delayed component came from the CME-driven shock propagating through the corona and interplanetary space. The fluence, total particle count over the event duration, placed it above all subsequent events for particles over 30 million electron volts. Peak proton flux at energies exceeding 500 million electron volts reached levels not seen again until some of the Halloween 2003 events, and even then, GLE 05 remained the record holder for integral flux above 1 gigavolt rigidity. If that happened today, every satellite in low Earth orbit would take damage, single event upsets would cascade through electronics, memory bits would flip, processors would lock up, solar panels would degrade from accumulated radiation dose, the International Space Station would issue shelter warnings. Astronauts would move to the most heavily shielded modules, the Russian segment typically. And wait, polar flights would ground. ICAO guidelines require rerouting when radiation at flight altitude exceeds 80 microsieverts per hour. During GLE 05, will rise. Estimates suggest polar flight altitudes would have seen doses exceeding 200 microsieverts per hour. That's approaching annual background radiation limits in a single transatlantic flight. And it came from a source near the solar limb. Most of the particles went west of Earth. A dead center hit would have been worse. The beam would have been wider. More particles aimed directly at us. Proton flux at all energies would have doubled, maybe tripled. The ground level enhancement would have been visible on neutron monitors worldwide. not just the high-latitude European stations that caught the edge of it. Number 5, the fast-moving X-class flare with immediate effects. The flare itself is electromagnetic radiation. No mass, just photons, X-rays, extreme ultraviolet, radio waves, gamma rays. It travels at the speed of light, 8 minutes from sun to Earth. No warning. You see the flare. 8 minutes later, the radiation hits. The ionosphere on the daylit side of Earth absorbs it. D region ionization spikes. HF radio dies instantly. R-scale blackouts. R1 through R5. X-class flares are the strongest, classified by peak flux in the 1 to 8 angstrom wavelength band measured by GOES satellites. X1 is 10 times stronger than M1. X10 is 10 times stronger than X1. There's no upper limit. The biggest, directly measured, November 4th, 2003, X28 during the Halloween storms, but the sensor saturated. It peaked higher. Estimates put it at X45. The calculation comes from ground-based ionospheric measurements in comparison with similar events. That flare overloaded detectors in geosynchronous orbit. The X-ray flux exceeded 10 to the negative third watts per square meter. The radiation storm that followed was S4. The geomagnetic storm from its CME was G5. Wide area augmentation system went offline for 30 hours. Japan's ADOS-2 satellite permanently damaged. Multiple satellites lost orientation. Power grid operators reported voltage fluctuations but no blackouts. May 14th, 2024. Active region 3664, same region that caused the May 10th cannibal CME, fired an X 8.7. Most powerful flare of solar cycle 25 at that time. November 11th, 2025, X 5.1 from region 4274. Radio blackout over the Pacific and Americas, R3 level. Shortwave went dead for an hour. The flare produced a Type 4 radio sweep, long-duration emission indicating a massive shockwave propagating through the corona. The CME that followed launched at 1,500 kilometers per second. These X-class events come with a double punch. The flare hits immediately, 8-minute warning, ionosphere disruption, satellite sensor blinding, GPS signal degradation as the ionosphere changes thickness. Then 12 to 72 hours later, the CME arrives with its geomagnetic storm. You can't hide from the first hit, but you get hours to days to prepare for the second, unless it's a really fast CME. August 1972, X20 flare. CME arrival 14.6 hours later. In that case, you get 14 hours to shut down transformers, orient satellites into safe mode, and evacuate astronauts to shielded areas of the station. Number 6, the long-duration geomagnetic storm. This isn't one hit, it's a siege. Earth's magnetosphere gets compressed and doesn't recover. The ring current, charged particles trapped in Earth's magnetic field between 7 and 9 Earth radii altitude, intensifies. Normally it's weak. During a storm, solar wind particles get injected. The current strengthens. It generates its own magnetic field pointing opposite to Earth's. The disturbance storm time index goes negative. Negative 100 is strong. Negative 200 is severe. Negative 371 is May 2024. The record, September 1st and 2nd, 1859. The Carrington event, estimated negative 1760 nanotesla, maybe lower. Measurements came from the Calaba Observatory magnetometer, one station providing data. The aurora reached 18 degrees magnetic latitude, blood red in color. So bright in the Rocky Mountains that gold miners woke up thinking it was morning and started making breakfast. Telegraph operators got shocked by current induced in the wires. Papers caught fire. Telegraph stations in both the United States and Europe reported sparking, arcing, and equipment damage. Some operators disconnected the batteries and sent messages using only the current induced by the geomagnetic storm. That worked for hours. The event lasted from August 28th through September 3rd. 2 major auroral storms occurred. August 28th and 29th, September 2nd and 3rd. The second was significantly stronger. Richard Carrington and Richard Hodgson independently observed a white light flare on September 1st. That flare launched a CME that reached Earth in 17.6 hours precisely. Extremely fast. But why so fast? Researchers now believe a smaller CME on August 28th cleared the solar wind ahead of it. The September 1st CME traveled through a low-density corridor, no resistance, 17.6 hours. The magnetic field orientation was perfectly south. Maximum coupling. The energy released into Earth's magnetosphere was estimated at 10 to the 35th electron volts. That's 10 followed by 35 zeros, equivalent to a 10 megaton nuclear weapon. The aurora persisted for 42 hours during the September event. People in the Caribbean saw it. People in Mexico, Cuba, Italy. Ice core data from Greenland and Antarctica show evidence of similar events approximately every 500 years. The last comparable storm before Carrington was 1770. The one before that, around 1250. We're overdue. A Carrington-level storm today. Lloyd's of London estimated in 2013 that the cost to the United States alone would be $600 billion to $2.6 trillion. That was 15.5% of annual GDP at the time. The estimate assumed widespread transformer damage, months-long blackouts in multiple regions, cascading failures across interconnected grids, satellite losses, and GPS outages affecting everything from shipping to agriculture. Food production would drop. No GPS for precision farming. No refrigeration in large areas for weeks. Communication networks fragmented. 80% of high-voltage transformers in North America are over 25 years old. Custom-built, replacement time measured in years, not days. If multiple transformers blow across different regions simultaneously, there aren't enough spares. Number 7, the Miyake event. This is the nightmare. The one that doesn't show up on magnetometers because it happened before magnetometers. It shows up in tree rings. Carbon-14 and beryllium-10 isotopes spike when cosmic rays hit the atmosphere. Normally, the levels are stable. Galactic cosmic rays trickle in at a steady rate. But sometimes, rarely, the isotope levels jump. Sharp, big, 774 to 775 CE. The carbon-14 concentration increased 1.2% in a single year. That's 12 parts per thousand. Unprecedented in the modern record. Japanese physicist Fusa Miyake discovered it in 2012 analyzing tree ring data. The event is named after her. Researchers found similar spikes in ice cores from Greenland and Antarctica. Beryllium-10 jumped in sync. The cause? A massive solar proton event, maybe multiple events in rapid succession. The 774 event was at least 10 times stronger than the Carrington event. 20 times stronger than any directly measured solar storm. 6 more Miyake events have been identified. Approximately every 1,000 to 1,500 years, one hits. 660 BCE, 994 CE, 1279 CE, 1190 CE, 1443 CE, 5800 BCE, the strongest, 14,300 years ago, found in tree samples from the French Alps. That one dwarfs everything. The isotope spike indicates the most violent solar storm ever detected. If a Miyake-class event hits now, the electromagnetic pulse alone would destroy satellites in the tens of thousands. Low Earth orbit, geostationary, everything in between. GPS gone, communication satellites gone, weather monitoring gone. The ground-level radiation would spike to levels comparable to the 1956 event, but sustained over days instead of hours. Power grids? Forget it. The induced currents would blow every high-voltage transformer on the daylit side of Earth. Geomagnetically induced currents, measured in hundreds of amperes per phase. Transformers aren't designed for that. They'd saturate, overheat, and fail in minutes. The blackout would last months, maybe years in some regions, because you can't just swap in a new transformer. They're custom-built for specific locations, weigh hundreds of tons, take 12 to 18 months to manufacture. You'd need hundreds. At the same time, while the factories have no power, the economic cost? Immeasurable. Not trillions. Trillions assume you can rebuild. A Miyake event could collapse modern technological civilization for a decade. And the frequency? These events occur roughly every 400 to 2,400 years, according to research published in Astrophysical Journal in 2022. Other research looking at sun-like stars across the galaxy suggests large superflares, bigger than Carrington, may occur every few hundred years. We have records going back 10,000 years. We've seen 7. That's an average of 1 every 1,400 years. But averages mean nothing. They could cluster. 3 in 500 years, then nothing for 3,000. We have no way to predict them. Can't see them coming. The first sign would be satellite failures across the board. Then 8 minutes later, the ground level effects. By then, it's too late. You can't shut down the grid in 8 minutes. Can't shield satellites. Can't warn aircraft. It just hits. So where are we now? Solar cycle 25 peaked in October 2024. Solar maximum. That's when magnetic activity on the sun is highest. Most sunspots. Most flares. Most CMEs. The peak of cycle 24 was in April 2014, with a smooth monthly sunspot number of 116. Weak cycle. Cycle 25 is stronger. Peak sunspot count between 137 and 173, according to NOAA's revised forecast. We're seeing X-class flares regularly. Multiple G4 and G5 storms in 2024. More in 2025. As of November 17th, 2025, over 50 X-class flares have fired this year. Active region 4274 alone produced 3 X-class events in 3 days. X 1.7, X 1.2, X 5.1, November 9th, 10th, and 11th, each with an accompanying CME. The forecast models showed them merging into a cannibal structure. G4, watch, maybe G5. The peak will last through 2026. Then activity drops. Cycle 26 begins around 2030. But even during solar minimum, the big ones can still hit. Coronal holes dominate. High-speed streams. Recurring G1 and G2 storms every 27 days. The question isn't if, it's when, and how big. You can't stop the solar storm, can't shoot it down, can't deflect it. You can only prepare. Satellite operators orient solar panels edge on to reduce surface area during radiation storms. Power grid operators load shed before impact to reduce current flow. Airlines reroute flights away from polar regions. Astronauts shelter in the most heavily shielded modules of the station. GPS receivers switch to backup signals. All of this requires warning. The AC satellite, Advanced Composition Explorer, sits at L1, 1 million miles from Earth between us and the Sun. It measures solar wind speed, density, magnetic field orientation. When a CME hits ACE, we get 15 to 60 minutes of warning depending on speed. That data goes to NOAA Space Weather Prediction Center. They issue the watches, warnings, alerts. Power companies listen, satellite operators listen, airlines listen, but ACE launched in 1997. It's old, running on backup systems. The replacement mission, DISCO-VR Deep Space Climate Observatory, launched in 2015 ITAS, is already there, but it's a weather satellite repurposed for space weather. Not purpose-built. We need better. Multiple satellites at L. 1. Redundant measurements. Faster data links. Right now, a big CME takes out ACE on the way in. We're blind. No warning. That's happened before during smaller storms. Sensors get saturated. Data corrupts for 15 minutes to 2 hours. Nothing. Then the storm hits Earth, and we're guessing. Here's what breaks first. GPS. Not the satellites, they're hardened, but the signals. The ionosphere thickens and thins unpredictably during a storm. GPS assumes a stable ionosphere. It's not. Position errors grow from meters to kilometers. Precision agriculture stops. Autonomous vehicles can't navigate. Shipping routes rely on GPS timestamps for navigation. Those go bad. Power grids are next. High voltage transmission lines act like antennas. The changing magnetic field induces current, direct current. Transformers are designed for alternating current. DC makes them saturate. The core overheats. Insulation fails. The transformer explodes or just dies. You've seen one blow, loud, spectacular, unrepairable. In a Carrington-class event, dozens blow simultaneously. Grid operators try to disconnect sections to isolate damage, but the cascading failures move faster than human decisions. 9 hours to restore power in Quebec in 1989. That was 66 substations offline at once. Double that number, triple the geographic spread, and you're looking at weeks minimum. Satellites in low Earth orbit experience atmospheric drag increases. The storm heats the upper atmosphere. It expands. Density at 400 kilometers. Altitude triples. Satellites slow down. Orbits decay faster. Operators burn fuel to reboost. If the storm lasts days, some satellites run out of fuel. They fall. Uncontrolled re-entry. Satellite collisions generate debris. Debris hits other satellites. Kessler syndrome. Cascade. In the worst case, low Earth orbit becomes unusable for decades. The Carrington event happened in 1859. Global population under 1.3 billion. Most people lived on farms. No electricity, no satellites. Telegraph was cutting edge. It broke. Life went on. Now, 8 billion people. 50% live in cities. Total dependence on electricity. Food supply chains require refrigeration. Water treatment requires pumps. Hospitals require power. If a Carrington-class storm hits the United States, Europe, and Asia simultaneously, daylit hemisphere, and takes down the grids for months, the death toll isn't measured in thousands. Millions? Starvation, disease, societal collapse in urban areas, and the last big one was 1859, 166 years ago. Ice cores say they happen every 500 years on average. We're in the window. July 23rd, 2012. A Carrington-class CME erupted from the sun. X-class flare. CME traveling at 2,900 kilometers per second. It missed Earth by 9 days of orbital position. 9 days, 1 week, and 2 days. If Earth had been there, it would have hit us square. Stereo A spacecraft caught it. The magnetic field strength, particle density, and speed all matched 1859 levels. Researchers at the University of Colorado Boulder published the analysis. That storm would have caused multi-trillion-dollar damage and year-long blackouts in multiple countries. It missed. We got lucky. You want the summary? 7 types. High-speed streams from coronal holes, minor, persistent to predictable, isolated coronal mass ejections, moderate to severe, 24 to 72 hours warning, cannibal CMEs, severe to extreme, amplified effects, complex magnetic fields, solar radiation storms immediate, penetrates to ground level in extreme cases, radiation hazard at altitude, X-class flares with radio blackouts, 8-minute warning, immediate ionospheric disruption, long-duration geomagnetic storms, days of magnetosphere compression, transformer damage, satellite loss, Miyake events, catastrophic, civilization ending if it hits now, happens every 1,000 to 1,500 years. We've measured solar storms for 77 years, cycle 19 through cycle 25. In that time, the worst was May 2024, G5. Before that, Halloween 2003, G5. Before that, March 1989, Quebec blackout. And before that, August 1972, fast CME. Before that, February 1956, ground level enhancement 05. Before that, Carrington 1859. We have records of 6 events in 77 years that reached G4 or higher. That's one every 12.8 years on average. We have records of Miyake events and tree rings showing 7 in 14,000 years, 1 every 2,000 years. The sample size is laughable. Trying to predict solar storm frequency from 77 years of data is like trying to predict earthquakes from a weekend of seismograph readings. But here's what we know for sure. The sun is not done. Solar cycle 25 continues into 2026. We've already seen 3 cannibal CME events in 2024. November 2025 is shaping up for another. X 5.1 is the biggest flare of the cycle so far, but we're not at solar maximum anymore. We're past peak, in the declining phase where activity should decrease. It's not active region 4274 stayed active for over 2 weeks, crossing the disk, firing M-class and X-class flares continuously. Region 4284 just emerged near disk center. 14 of the 15 flares in the past 24 hours on November 17th came from that region. The sun isn't calming down. Researchers at NASA Goddard Space Flight Center, publishing in May 2024, said they'll be studying the May 10th event for years. Teresa Neves Chinchilla, acting director of Moon to Mars Space Weather Analysis Office, called it a benchmark. The British Geological Survey said the October 10 2024 G4 storm could have been one of the biggest in 20 years. ESA's swarm satellites measured magnetic perturbations greater than May 10th at specific latitudes. The data is still being analyzed. We don't have the full picture yet, but the storms are intensifying, and the grid is old, and the satellites are fragile, and we've been lucky. In 14,300 years, the biggest solar storm on record hit. Trees in the French Alps recorded it. No one was there to see it. No cities to burn out, no grids to collapse. Just trees, quietly encoding the radiation signature in their rings. Waiting 14,000 years for us to find it. The next Miyake event could fire tomorrow. Could fire in 3,000 years. We don't know. Can't know. The only certainty is it will happen. And when it does, the 8-minute warning won't matter. Because by the time you see the flare, the radiation is already crossing the 93 million miles. Already ionizing the atmosphere. Already wrecking the satellites. Already inducing current in the grid. And all you can do is watch the auroras, red, green, purple, shimmering across the entire sky. Visible at noon, and know that everything just changed.